Thank you. Thanks everyone for joining after the lightning talks, and great to be back here at stackconf. And today I'd like to talk to you about metadata, the secret sauce for full observability. So we all know observability. The formal definition is a measure of how well internal states of a system can be inferred from knowledge of its external outputs. And these external outputs are, as you can see on the screen, the telemetry data that our systems emit, primarily logs, metrics, and traces, but it can also be other signals such as profiling and others. That's why I don't really like that Venn diagram that shows it's only these three. But definitely this telemetry data is the basis for observability. And metadata is the data about the data. It gives us additional context about our telemetry. This could be technical context, such as the IT environment, production, staging, smoke testing, whatever. Or it could be also business context, such as which customer account from which the request is invoked, or things like that. And metadata helps us turn our logs or other telemetry into meaningful events. My name is Dotan Horovits. I'm the principal developer advocate at logs.io. Logs.io provides a cloud-native observability platform that's built on popular open source tools, some of which you've heard today, such as Prometheus, OpenSearch, OpenTelemetry, Jaeger, and others, and offers that as a managed service built for scale. So if you have any questions about logs.io, we don't have a booth here or anything, but feel free to talk to me after the talk. That's not the topic of this conversation. I'm also a CNCF ambassador. CNCF is in the Cloud Native Computing Foundation, where Kubernetes is, and Prometheus, and OpenTelemetry, and many other projects that you know and love. So if you have any questions about CNCF and Cloud Native Stack, also happy to talk after the talk. And I also have a podcast called Open Observability Talks about these topics: open source, DevOps, observability, platform engineering, and the likes. I already have a new fan here that joins over lunch, so ask him. He can tell you. And you can find me everywhere at Horovits, so Twitter, LinkedIn. One of the folks here said that he likes the fact that I'm on Mastodon, so I'm on Mastodon as well. Medium, YouTube, whatnot, just look up Horovits. So I'm saying that metadata is important, but it starts from something much more fundamental. Observability is a data analytics problem. And this is something that I've been talking about all over the world for quite a few years. There are articles of me talking about that from a few years back already. And this is fundamental. Actually, advocate for a new definition for observability, not the old one that is actually taken from applied math, from control theory, but one that will be strictly for software. And it is observability is the capability to allow a human to ask and answer questions about the system. Of course, based on the telemetry that the system emits, but the ability to ask and answer questions. That's data analytics in a nutshell. And the more questions we can ask and answer about the system, the more observability is. And again, there's the article I wrote at Inside Big Data a few years back about that. So if you want to scan the QR code, more about that. And once we understand that observability is about data analytics, the importance of metadata becomes clear. And in fact, for those who come from the data space, there is a whole parallel universe called data observability. And in the data observability domain, you can see that metadata is in fact positioned as one of the pillars. And we can definitely learn from that domain. So that's I hope, to convince you that metadata is important and even crucial. And now that we understand that, let's talk about what metadata is. So metadata gives us the context on the entity producing the telemetry, whether on the infrastructure resources or on the application code. When we talk about infrastructure, this metadata could be things such as the geolocation, the environment, as I said before, instance name, host name, cloud region, or whatnot. That's let's say, the basic ones. And then we can also add custom metadata. What typically happens is that operations teams, ops teams, often tag the underlying infrastructure, the underlying machines, Kubernetes nodes, and so on, and with resources, labels, annotations that provide additional denotion, and that could actually provide additional metadata, infrastructure context that we can add as metadata to our telemetry. That's on the infrastructure level, and on the application level, metadata can give us a wide range of context on what goes on in the code itself. Some of that comes out of the box. For example, all sorts of instrumentation libraries provide basic out-of-the-box context about the module, package, class that emitted that telemetry. And also, of course, in addition, our developers can add custom metadata relevant to the business logic that they themselves develop. And once we have that metadata in place on our telemetry, then we can apply data analytics on it. All the things that you'd expect, do a filter, group by, define alerts, run queries, everything that you do with data analytics. So now I want to look into the various telemetry data types and see how they can be enriched with relevant metadata. And let's start with logs, the most long-standing and well-practiced telemetry, and talk about how we do log enrichment with metadata. And this is a question for the audience. How many of you who still has these kinds of unstructured plain text logs somewhere in its system? With a show of hands. Be honest. Okay, look around you. And I'm here to tell you, don't. So forget about unstructured plain text logs in flat files. Assume that no human is going to read through your mounts of log lines to extract insights. Okay? As I said, observability is about data analytics, and we need the logs to be structured, strongly tight, machine readable, so that we can use software to analyze it at scale. So your logs should probably look more something along these lines, and as a best practice. And it's important to say, metadata is a big word, but some logs come with basic metadata out of the box. So we can see, obviously, log level. We can see timestamp in a very well-defined format. So this is also metadata. We don't think about it, but this is something that we get as part of the log appender or whatnot that you use in your system. So that's a good start. And it's important for you to also model what you need. So remember, observability is a property of your system. You need to apply what I call observability-driven development and be thoughtful about building sort of the schema or modeling all the relevant data into your log metadata. So use structured logs and also make sure that you use consistent conventions. So not service underscore ID in one place, service ID camel case in another, customer ID in another. Use observability-driven development to set these conventions. And actually in large organizations, I see platform engineering shaping up, becoming popular, and many actually use platform engineering to help create these cross-organizational conventions and specifications that can help provide abstraction layers even, that the developers don't need to be bothered with that. They get it out of the box as part of some facilitation that platform provides them. So very interesting benefit from platform engineering. I have a whole talk a couple of weeks ago. I gave a talk in Prague in Kubernetes Community Days just about platform engineering. Whoever wants to talk about it, curious to also hear how you do that. But essentially, this is the basic metadata. And then on top of that, we can add metadata that we find valuable to investigate. So I gave here, based on the previous log, I added 2 examples, like user ID, okay? Having the user ID or customer ID or the build version can greatly help us map the logs into the root cause. So if you think about a customer-specific issue, wouldn't that be much easier to correlate when we have the user ID? Or if we have a problematic build and we have the build version as part of the metadata. So this is the principle, and remember, effective data enrichment can turn our telemetry into meaningful, and the log specifically in this case, into meaningful events. So that was about logs. And now let's talk about traces. Just out of curiosity, who uses distributed tracing in the organization with a show of hands? Okay. And who knows? Not doesn't use, but explored in one way or the other? Okay, so good to see that. So tracing is an interesting telemetry, because at the heart of distributed tracing lies the notion of the trace context and its propagation through the system. And the trace context is essentially metadata. So let's see how it works. I see that not everyone is familiar with tracing, at least hands-on. So just a quick recap. Trace obviously is the full record of activity of a request flowing through our distributed system. And on the left-hand side here, you can see its visualization is a directed graph. So a user called service A, then service A called service B, then B called C and D, and then afterwards E, where A, B, C, D are the specific operations within the trace, or what's known as the spans. So the span is one hop, if you wish, within the trace. So that's the basic notion, and the typical visualization of a trace is on a Gantt chart, like you see here, or a timeline view, where you can really nicely see which called which in the time sequence. You see how long it took by the length of the bar. You see which one ran in parallel and which ran sequentially. So it's very easy to understand the flow of the request through your system. So that's tracing in a nutshell. And then, as I mentioned, at the heart of the tracing, there's the notion of the context, which is the data required for moving the trace information across service boundaries. And the context consists of different metadata. It could be global unique identifiers, such as the trace ID and the span ID, and so on. It could be the operation name, the start time, the duration of the execution, the parent-child relationship, and so on. This is the base context that is typically there. And as I mentioned, I can't stress it well enough, context is crucial for distributed tracing, much more than in other types of telemetry, and really the power of distributed tracing lies in the context. So that was the basic context, but in addition to the basic context, the application can then add a lot more context into the mix. Some people ask me over lunch, what could it be and what can be captured? So if you want to capture the URL of an HTTP request or the SQL statement of a database query, whatever you do with your instrumentation, you can capture as additional metadata on top of that. So, and the context is propagated through your system. There's a mechanism for that moves this information across boundaries, process, thread, service boundaries. Moves that. Typically, it's done with HTTP headers. There's a whole spec, W3C spec for that. I won't be bothering you with that. Typically, you won't be bothered with that either because the instrumentation libraries will do that for you, but just so you know how the context is propagated. And now that we understand that, and now that we have the system instrumented, then we get, in the backend, the ability to use this metadata in our day-to-day. So this is the Jaeger UI. Jaeger is an open source under the CNCF, so being also a CNCF ambassador, happy to show you for those who don't know. And in the Jaeger UI, you can see how it's built. On the left-hand side, you can see the indented way. You see front-end calling customer, and then customer calling MySQL. It's very easy to see the flow. And then in this part, you can see the spans, the length of the bars. And here I expanded the MySQL span, so you can see metadata. You have different types of metadata. I think the most interesting is here, for those who can see, SQL query, select star from customer, where customer ID equals 1, 2, 3. So you can really see the metadata bundled within the trace context. So this is how it looks like. When you already have that instrumented, you can use that in your analytics backend. In this case, Jaeger UI and the Logs.io managed service. So that's tracing. And now let's talk about metrics. So with logs and traces, we saw a lot of inherent metadata. We saw logs come with log level and timestamp and other metadata, environment we saw, and so on. With traces, we saw the operation name, the duration, the span ID, and so on and so forth. Unlike logs and traces, metrics are essentially numerical data points with very little context or metadata. So in the context of metrics, the data enrichment is even more crucial. The good news are that many metrics collection agents provide out-of-the-box metadata enrichment of metrics based off of the information that the agent gathers about the environment. So typically these agents run co-located with the application on the same node, on the same pod sometimes, with direct access to the environment and can collect a lot of information. For example, in Prometheus case, how many use Prometheus? Okay, so a lot of you. So in Prometheus case, they have, you probably know, the Prometheus service discovery mechanism that automatically detects the scrape targets, the components in your system. And then Prometheus can then add this metadata as labels to the metrics that it emits. So let's look at the example of Kubernetes. In Kubernetes, Prometheus has the Kubernetes SD, Kubernetes Service Discovery, which exposes metadata for various Kubernetes resources, such as node, service, pod, endpoint, and ingress. On this slide, you can see just a tiny bit, just an example of the Kubernetes node resource type with a node name, what we can see here, a node provider ID, node address, and so on. Another interesting thing that I brought this example for is to see, in addition to the out-of-the-box Kubernetes metadata, we can also have custom metadata. I talked about it before that many ops teams annotate or tag the nodes with logical classification or other context. And these annotations and labels on the node are also added as custom metadata to the metrics themselves. So we can see here the labels and annotations. Each annotation that you define will have the annotation added in this convention. So metadata Kubernetes node annotation and your annotation name. Okay, and also if it exists. So you can see whether it exists and the value. Whether it's present and the value, same for labels. So you can add your own custom metadata. And obviously this is not just for Kubernetes. Prometheus provides a wide range of service discoveries for other infrastructure types such as AWS, EC2, Azure, Docker, and many others. So, and obviously also other tools, not just Prometheus, provide this capability to enrich. And once you have that metadata in place, it's easy on the back end to filter by customer or node and to segment the metrics. For example, here at the bottom, I don't know if you can see the CPU utilization and CPU load graphs segmented by machine. So we have the metadata. We can now segment by that metadata. We can filter. In the top, you can see the cluster and so on. So really, this is how suddenly you have the abilities to do the data analytics based on the metadata. So far, we've explored the use of metadata to provide extrinsic context outside of our telemetry. Metadata can also help correlate between different telemetry signal types. And this intrinsic context is essential for breaking down the data silos and enabling cross-cutting queries and the true data analytics capabilities of observability. So let's talk about cross-signal correlation with metadata. And let's start with correlating traces with logs. So think about the scenario. We're investigating a trace, a request trace, and then we want to see the logs emitted, but the ones that are emitted to that by that specific request. Okay? And the service may be servicing, I don't know, tens of thousands of requests per second. We want that one that is in this specific context. So one common practice is to add the trace ID, that global unique identifier, as metadata to the logs to enable easy trace log correlation. A more advanced pattern is to actually emit your application logs as part of the payload or the metadata of the trace itself. So think about that microservice that invoke this operation. Today we send logs, we emit logs, and then we emit a trace, a span. Why emitting two signals for the same thing? How about we emit just a span and package the logs, and when being inside the span, they're inherently contextualized to that specific operation in that specific request. Another best practice is metrics trace correlation. So in this case, like you see here in the graph, we see suddenly, let's say, imagine a spike in the latency of on a specific endpoint. And then you say, obviously, the next step in the incident investigation is let's see one request, an example request of that high latency. So that's the use case, and the means here is what is called exemplars. And exemplars essentially means adding the trace ID as a metadata on the time series data, on the metric. For easy jump from the metric to a sample trace. And I'm glad to say that exemplars are by now pretty widely available and supported. Prometheus, OpenTelemetry, many other tools. So definitely something that is quite available. It's also useful to correlate events with our system status. So going back to the Kubernetes example and the use case, you can capture Kubernetes events via the Kubernetes API and plot them as annotations, as markers on top of the system metrics to see correlation. So I gave here an example where you see the pod memory suddenly at certain point in time becomes pretty spiky and erratic, and we might not understand why, but as soon as we turn on, you see there the switch to the deployment, and we mark the deployments, we see very clearly that it started right after we deployed a new version of the service to production. So this sort of correlation makes it very easy to see the change occurred right after the deployment was made. And similarly, we can triage issues following an update to a config map, deletion of a secret, or any other Kubernetes change to a Kubernetes resource that can be flagged as a Kubernetes event. So that's on Kubernetes. Obviously, we can also add other custom events of our choice in a similar fashion using metadata to create meaningful associations and to speed up incident investigation and root cause analysis. So we see the power of metadata and correlation. I hope I convinced you in that part. But how can we achieve consistency of the metadata across different telemetry sources and types? So let's say we want to investigate a given Kubernetes node and to ask and answer questions. Remember the definition of observability across the different telemetry sources and types. And also remember that some of these logs and metrics come from a third-party libraries. So even if we manage to create some consistent organizational conventions, these don't cover all bases, right? So we need to standardize on metadata to get effective correlation and investigation across our system and across our tech stack. So I'd like to look into standardizing on metadata with OpenTelemetry. Just a quick question, how many know OpenTelemetry with a show of hands? Okay, and amongst you, leave your hands up. How many of you show their hands also use that in production today? Okay, less so. So a word about OpenTelemetry. Good thing I prepared this slide. Very briefly, OpenTelemetry is an open source framework and a standard for gathering and collecting telemetry across the different telemetry types, logs, metrics, traces. We recently added continuous profiling as the fourth signal. It's an open source project under the CNCF, the Cloud Native Computing Foundation. And I'm proud to say, not just because I'm a CNCF ambassador, that the CNCF is today the most active project in the whole CNCF after Kubernetes itself. So Kubernetes is number one, OpenTelemetry is number two, and it's been consistently the number two for a long time. So very, very active project. And the framework includes instrumentation SDKs, a collector, an OTLP protocol, and other pieces. In that case, I want to talk about the open unified specification that OpenTelemetry defines for the data, which enables consistent metadata across logs, metrics, traces, and other signals. So this consistency enables cross-signal correlation, such as isolating all the signals originating from a given node, or to find logs for a given trace, and all these use cases in a standardized manner. So let's talk about how it's done. So OpenTelemetry specification defines attributes in the OTel name. That's the metadata, effectively key value pairs that represent different types of metadata. It could be signal attributes, instrumentation scope attributes, resource attributes with their respective semantic conventions. So again, let's look at the Kubernetes example. OpenTelemetry collector, if you remember, I mentioned the OpenTelemetry as a collector component. So the collector has a Kubernetes attributes processor that you can see here, the configuration, that automatically adds Kubernetes metadata as resource attributes on metrics, logs, and spans the trace data. So here we can see in the example the Kubernetes metadata that it can set. We see in the example the pod name, UID, start time, namespace, deployment, node name, and so on and so forth. The thing that you would expect. And again, consistently with the same naming across logs, metrics, traces, so on. And with our telemetry enriched with this standardized metadata, we can now use it in our data analytics at the back end. So things that we, for example, we can do a filter by, you can see that here on the left-hand side, filter by cluster, namespace, deployment. You see the list of deployments. You choose which one is interesting for you for the investigation. You can look into a specific view, like this in the top part, you see the view, so you can look at the deployment view, you can look at the workload, stateful sets, node view, and so on and so forth. And you can zoom into specific aspects of your system. You can look at the CPU, the memory, the restarts, the log error rate. So you decide, again, how to dissect, slice and dice your data depending on what's your incident investigation path taking you. And obviously, again, Kubernetes is popular. I know everyone mentions Kubernetes here in the conference, but Kubernetes is just one example. OpenTelemetry collector supports many other infrastructure types, such as Docker, Heroku, OpenShift, and so on, AWS, Azure, GCP, whatnot. So definitely a rich platform. And let's summarize. So, as I mentioned, and remember that observability is a data analytics problem, and is any data analytics problem, metadata plays a key role. So logs, metrics, traces, and other telemetry data, this is the observability raw data. Metadata is the data about the data. Okay? So we talked about enriching logs, metrics, traces with extrinsic data, whether infrastructure, application, technical, business, FinOps, security, whatnot. We talked about adding intrinsic data, metadata to support cross-signal correlation, like trace ID on logs or exemplars on metrics. As I mentioned, standardize your data. Start with organizational conventions and then use open standards such as OpenTelemetry. Check out this guide that I wrote on metadata for observability that gives a lot more information, so feel free to scan it. And remember, effective data enrichment turns telemetry signal into meaningful events. I'm Dotan Horovits, and thank you very much for listening. And question time.
Yes. Any questions? Yes. Here.
Hello. Very interesting stuff. Can I share my pain points? I wish operators could take metadata more seriously when it comes to cardinality. It's very often the case you are implementing an operator to your cluster, and then suddenly they have metadata, pod name in there, or IPs in there, and they use these as labels. So it's working fine, but then when they scale to hundreds of nodes, then suddenly you're having cardinality problems. And it's getting very expensive to search, very difficult to make, and you don't have any power over it. You know what I mean?
So what's the question? I identify with I empathize with the problem, but what's the question?
What can we do? How can we persuade the operators that cardinality is a proper problem and they should treat metadata as a way to solve things? Is there anything we can do about it?
So first of all, you can always pressure you pay them, so you can definitely pressure them and tell them you need to take. I have a whole different lecture about data analytics that I talk about the problem, what I call the data to noise ratio, the fact that we are flooded. Like any data analytics problem, we also get the problem of big data with volumes exploding. So that's dimensionality, and the cardinality obviously is the metric side, but as you said. And here, my recommendation, at least the one that is under your control, is going back to the basics. Apply observability-driven design and observability-driven development. Don't collect metrics, and not even labels on the metrics that you don't use. Many I see that just take the out-of-the-box, like Kubernetes users, take all the defaults, and Kubernetes has explosion of metrics and labels, and 75% of the metrics that come default, users don't use. Actually, I think I saw that in one of the vendor stats. Okay, don't just go with the defaults. Think about what you need. And if you have a metric that you never use in any dashboard, any alert rule, any query, anywhere, just don't persist it. Don't even maybe generate it or collect it. So that's the best practice. When it's your application, it's easier. When it's a third party, you need to approach the vendor and pressure them and explain to them that you're paying for the cost of the storing that afterwards. But definitely it's a challenge, the bloat of data in the data analytics space in general and in observability in particular.
Thank you.
Thank you. We're a little bit out of time, so maybe only one question. A short one? Okay, yes.
Nice catch.
Great catch.
Yes, I have a question, Dotan. What's your opinion on open feature for further enriching metadata in the observability space?
So for those who don't know, Open Feature is an open source for feature flagging. It's also under the CNCF, just for context for the audience. So it's another source when you talk about observability. It's just another source of knowing your domain. So your instrumentation will know, the basic instrumentation will know about which class emitted and which file and so on. Open Feature goes one level up and knows the context about which feature invoked it, maybe even which version, or A/B testing, so which type of the A/B. So it just adds another layer. I talked about whether technical or business, so this is something in between product-related metadata. very well established for the product and UX types of observability that are needed. And I have, by the way, a whole article about observability for product and UX and SaaS types of, PLG type of startups that need to measure bottom-up motions. That's crucial, these sorts of information.
Okay, now we are out of time. For more questions, please catch him at the hall. Thank you very much, Dotan.
Thank you, everyone.